All right, this inquiry is a fairly easy setup. We're going to be rolling a ball down this ramp, and we're going to measure the time it takes to go from certain distances down the ramp. So we're going to start 20 centimeters, and then the second photo gate here, we'll unclamp it and we'll move it down about 50 centimeters more, and so we'll be going 70 centimeters, and then we'll just keep doing that all the way down to I think about 4.2 meters. So we're going to have different times. The photo gate clicks on and then off with the second photo gate, and that'll just give me a time here that it takes to go between the two photo gates. So we'll have increasing distances, and then we'll have increasing times, and then we'll use that for our graph. Okay, so the first one we're going to do is we're going to do 20 centimeters. So we'll put it on here and we'll let it roll, and I'll catch it, and the time was 0.653. 0.653. I can clear it. I'll do it again just to check, see how close we are. 0.653, still good. Okay. All right, this is 70 centimeters distance. 1.292. Okay, 1.2 meters. 1.703. 1.7 meters. 2.039. 2.2 meters. 2.304. 2.7 meters. 2.568. 3.2 meters. 2.826. 3.7 meters. 3.019. 4.2 meters. 3.201. The first thing we're going to do is we're going to make a displacement time graph. And if you know what acceleration looks like on a displacement time graph, you should kind of predict what this graph should look like. So I'm going to highlight these two columns. I'm going to insert a chart. And if I can shrink this down here a little bit. So I get something like this. And that's good. That's what we predicted. If you go to customize and you go to series, we want to actually put a trend line through it. But the kind of trend line we want is not linear. That's a polynomial. It's a polynomial, and you'll see that it fits really good. It's almost every single dot on there. In fact, if we came down here just real quickly and did an R squared value, you see the R squared is actually 1. So that's a really good polynomial curve there. We do want the equation on here. So we're going to, let's see, come down under custom label. It's always hidden. In our label, use equation. And so we have an equation there, okay? And I'm going to write that. So if you remember the equation for acceleration on a displacement time graph, it would be this. It would be d equals 1/2 at squared plus vi t. So that's the equation for, and that's why it's a polynomial. It's a y equals x squared plus x plus constant kind of graph. And so the actual equation that we have on there is d equals, and then we have 0.4. I'm going to do the last part first. This part right here, 0.4x squared. So the x, remember, it was t. So 0.4 t squared plus VIT, which would be 0.019 0 to 0, 1 t. And you'll notice that there's also then a plus really, really small number, 6.78 times 10 to the negative third. So it'd be like 0.00678. So that is actually an initial displacement. This equation actually comes with another plus here, but normally what we're assuming is that our displacement is 0. Wherever we're trying to start from, we're assuming that that's our reference point. So normally there's an initial displacement at the beginning, and that initial displacement, of course, is 0. We would say that that's 0. Okay, and so this technically displacement down here is the final displacement. Final displacement. So if we do the final displacement minus the initial displacement, bring it over the other side, that's called a change in displacement, which is what this really is, change in displacement. So we're just gonna ignore this initial displacement. It's really hard to get it to be perfectly, there's a little bit of room that it rolled right before it started that first photo gate, but that's what that is. So we're just gonna ignore that section of it. Okay. Good. There's my first graph that I wanted to make. I'll move that up here somewhere. It's my displacement time graph. It's a curve. Okay. Now what I want to do is I want to get the velocity. Okay. So I want to figure out the velocity at every single one of these points. How would I do that? Well, if you remember your calculus, we can take the derivative of this first equation. The derivative of displacement is velocity, and if you remember, it's 2, the exponent times the coefficient. So 2 times 1/2 a would be a t to the first power, plus you take 1 times vi, it'd be vi, and the t then goes away, and there is our derivative of displacement, is this equation right here. Okay, so what's the derivative of this equation of this polynomial curve that we actually have? So it'd be the final velocity, or the instantaneous velocity would be, I would take 2 times 0.4, that's 0.8 t, plus 1 times 0.0201 would be plus 0.0201. Okay, so to figure out the velocities at every single one of these points here, I can actually now use that equation. So equals 0.8 times, grab the t, and then plus a 0.0201. That's an initial velocity. So there was actually an initial velocity because it was moving ever so slightly before it hit that first photo gate. So I'll hit return on that. I'll take that down, and so see at time 0 when it went to the first photo gate, see it was already going this speed. Okay, so I'll take that velocities down, and now I'm going to grab the time. I'm going to grab the velocity column. On the Mac, you have to hold Command down to do that. And then I'm going to insert a chart. And don't want that. Come up here. Let's get a scatter. Where's the scatter at? Scatter. And I'm going to have to do something else too. I'm going to use column B as labels. And let's see here. Okay, there we go. And I'm going to go to Customize. Let's go to Series. And let's do a trend line through this. Now this time, this is a line, right? So this equation over here, y equals mx plus b. See, it's a straight line equation. This was a second order polynomial, so it was a curve. Acceleration is a curve on a displacement time graph. But velocity is a straight line, so it's y equals mx plus b on this one. Okay. So we're going to do a trend line. We got the trend line on there already. It's going to be linear this time. Let's use an equation. And of course, the equation this time is 0.8 t plus 0.0201. We know what that equation is because we actually programmed it in to have that equation. Okay, so that is a velocity time. I'm going to click on this and change this, v versus t. There we go. Okay, so the last thing I want to do is acceleration. So how do you do this? Well, you take the derivative of velocity, and that would be acceleration equals, and then you take, you know, the one on this t right here times the a would be a. So what that means is a is just a constant, right? A is this constant acceleration. That's what this ball was doing. It was constant acceleration. So the derivative here, so the acceleration here equals 1 times 0.8. The acceleration is 0.8 meters per second squared is my constant acceleration. So what I want to do just here is just do equals 0.8, and I can drag that down. And I know this seems kind of ridiculous, but I'm gonna hold Command down. I'm gonna graph acceleration and time, insert a chart, and we want a scatter chart again. And I'm going to have to use column B as labels. If you ever get these two lines, use column B as labels. Okay, and I'm going to get a straight line there, obviously. I'll go ahead and do customize. I'll do series, trend line, and I'll use the equation, but we already know what that is. It's going to be A equals 0.8. Don't worry about this thing of the x here. It's like it's basically 0. Okay. Well, let's change this again. This is acceleration versus time. I got acceleration time graph there. I'm going to put it right there. Okay. All right. So what we learned here is if we take the derivative of that, we graph displacement versus time. That was acceleration on a displacement time graph is a nice curve right here, a polynomial curve, and it's given by this equation. And we actually figured out what our actual equation was for our particular acceleration, and it's this right here. We take the derivative of that, and you get a y equals mx plus y equals mx plus b equation, which means a straight line on a velocity time graph. Acceleration is a straight line on a velocity time graph. And then we took the derivative of that, and we get a constant. So acceleration on the acceleration time graph is constant. It's just going to be a horizontal line at a 0.8. Okay, so what we want to do here is a little tricky. We want to now integrate these curves. So we want to go backwards. So the derivative of displacement is velocity. The derivative of velocity is acceleration. What is the antiderivative or the integral of acceleration? Well, then it'd be velocity. What's the antiderivative or integral of velocity? Well, it'd be displacement. And we want to kind of show that here. So the way you integrate a curve here is you find the area. What that means is finding the area underneath the curve. So we're going to integrate this acceleration time graph up to like 3 seconds. In fact, let's pick one up in here. Let's do 3.019 seconds. So we're going to integrate this curve up to 3.019 seconds. And we're going to find out what's the area underneath this graph, because that should end up being the velocity. So if I do that, this is a rectangle here, right? It's a rectangle, and the base of the rectangle will be 3.019. We're going to go all the way over to here, and the height of it is 0.8. So I'll take 3.019. So I got a rectangle basically, and the base is 3.019, and the height is 0.8. So if I multiply those together, 0.8 times 3.019, okay, I get 2.4152. Now what you have to remember is that is not including an initial velocity. So there was some initial velocity. So I'm going to add on plus 0.0201, and I get a velocity at time. So at time 3.019 seconds, the instantaneous velocity should be 2.4, basically 353. And if you look here at the 3.019, that's what the velocity is, 2.4353. So I found that by finding the area of this rectangle up to 3.019, and then I added on the initial velocity, and that gave me the instantaneous velocity at 3.019 seconds. Okay, now, so that means if I come over on this graph, and I look at 3.019 seconds, and I come up here, it would read 2.453 velocity at 3.019 seconds. Okay, so now what I want to do is I want to integrate this graph. So this is a velocity time graph I want to integrate. I want to find the area underneath this curve up to 3.019 seconds. So I'm going to, if I just redraw this graph here, I'm going to exaggerate a little bit, because remember this graph doesn't actually come down through 0, 0, because the initial velocity is actually 0.0201. So the y-intercept is right here, a little above 0. I'm going to exaggerate a little bit, go like this, so that I can make that point 0.0201. And then the line goes up like this. And so we're going to integrate this area of this all the way over to 3.019. We're going to find the area underneath this curve. And you'll notice that since I exaggerate a little bit, you'll see that there's a rectangle right here, and then there's a triangle. Okay, and so we want to figure out what the area is under that. So what's the velocity up here at this point? We actually figured that out already. It's 2.4353. Okay, and the velocity right here is 0.0201. So the area underneath this velocity time graph, the area underneath the velocity time graph should be the displacement that it has traveled at that time. So what I should have is D should equal the area of this triangle. What's the area of a triangle? Well, it's 1/2 the base, which would be 3.019. That's time, right? Times this height right here, times this height right from here down to here. That's a change in velocity. That's a change in velocity. It's the final velocity minus the initial velocity, so change in v. Okay, plus the area under the rectangle, which would be the height, which is initial velocity 0.0201, so vi, times the base, which would be the time. Okay, so you might recognize this as being, because you have this equation up here, that one right there. 1/2 at squared is actually the same thing as 1/2 delta v over t, right? Because what is acceleration? Acceleration is delta v over t, right? So delta v is a times t. So this section right in here would be 1/2 times t times a times t. And what is that? That's 1/2 a t squared. See, it's the same thing. Plus vit. So this section right here is actually the area of a rectangle. And this area right here is this section here is the area of the triangle. Okay, so if we figure that out, we're going to have 1/2 times the time, which is 3.019, times the change in velocity would be, I'll just do that in the calculator, 2.4353 minus 0.0201 gives me a 2.4152. Okay, and then plus the initial velocity 0.0201 times the time, 3.019. I'm going to run out of room here. Sorry, looks very bad. Okay, so I'm going to do 0.5 times 3.019 times 2.4152 plus 0.0201 times 3.019, and I get a displacement, a total displacement of like 3.7 meters. Okay, and if you go up here at 3.019, you look on the displacement time graph, and you come up here and you read across, you'll see, and you can just do it right here in the table, you'll see it's 3.7 meters. So what we've shown here overall is that the derivative of the displacement time graph is a straight line velocity time graph. The derivative of this is a constant on the acceleration time graph. If you go backwards and you find the antiderivative, the integral under the acceleration time graph, up to a certain point, you'll have the velocity at that instantaneous velocity at that time. If you integrate that curve, you'll have the displacement at that particular time on this particular graph. Okay, so that was a lot. Hopefully that helped with a little bit. If you understood the calculus lecture, then maybe that made a little bit more sense how all that works together.